Okay.
Yeah, please begin.
Okay, now we can start. So, good afternoon, everyone. I wish you all a very happy Bhai Dooj. I warmly welcome you all to day two of Currylip Days 2022. I am Chaitanya Sheth, a PhD student at MS University, and I am the host for the day. Today is a quite special day for Currylip Club as we turn 4, and our guiding light, Professor Kumarasan, turns 74 today. To mark this special occasion, we have two special speakers today. Right now, for the first talk, we have Professor Bhaba Kumar Sarma, a professor of mathematics at IIT Guwahati. Professor Bhaba has got his PhD from University of Delhi. He is an expert of combinatorial matrix theory, finite fields, and cryptography. He has several excellent publications in these fields. He has been associated with MTTS for the last 25 years. He is also a trustee of MTTS Trust. Today, Professor Bhaba is present here to enlighten us on the topic Invitation to Graphs and Matrices. It's really an interesting topic. During the talk, if you have any questions, please let us know through comments and we will request the speaker to answer it either during the talk or at the end. YouTube viewers may post their questions in the live chat. Thank you, Baba sir, for accepting our invitation. The floor is all yours.
Yeah, thank you, Chaitanya. Yeah, I thank the Kailif team for organizing this event. This is the uh, fourth chapter of this Kailif days, and the kind of activities we are having from this in this platform, they are very heartening. And today, actually, we are also celebrating the birthday of our beloved teacher and leader, Professor Kumaresan. I wish him a very happy birthday, and I welcome all of you for this talk. This talk, okay, as the title says, it is sort of an invitation to graphs and matrices. Of course, I mean it will be very uh, I mean elementary kind of talk. So we'll just try to see some relation between matrices, the linear algebra, and graphs. So graphs are okay, they are very widely used objects. So from many different fields, these graphs appear, and that's why you can see that same terminology. It has many connotations from many different angles. But nevertheless, so graph theory is a very useful area of mathematics, and even the theory of graphs itself is very interesting. So I'll just try to see very informally. I'll not be my lecture today will not be very structured. We'll just try to see some connections between graphs and matrices. Okay, how graphs can sort of very elementary thing. We'll see how graphs can appear as while dealing with matrices, and also how the matrices can give rise to various ideas or various properties in a graph. So essentially, that is what would like to see. A very maybe in a scattered way, we'll see a few things, few objects in in graphs, in matrices, and some relations between graphs and matrices. So let me start with the screen. Is my screen visible?
Yes, it is visible.
Okay. So let me start with this object called graphs. So graphs, I think, I mean, it is I mean, mostly known, and in fact, the name itself, and because it has a kind of drawings is involved in the graph, the name itself it suggests by a I mean graphical representation. So they are very natural to natural language. Graphs has very natural language. So here is what I have drawn. It is a graph. Okay. So what is a graph? So graph, you see that this I have some nodes here. So these are nodes, okay, and some nodes they are connected by line segments. So the essentially, so I mean, if I mathematically if I want to talk about a graph, what is graph? Graph is a pair. Okay, graph is a pair. So this pair is actually one is your V and one is E. Okay, so I'll be very pathetic in writing, so please bear with me. So G if I say G is a graph, graph means graph has two things, two objects. One is vertices. So it is V. V is the set of vertices, means these nodes. Okay. So this is a non-empty set. Okay, non-empty set. So it's a non-empty set. Usually, so this is a subset of your set of natural numbers. Actually, nodes are usually denoted by natural numbers. And E, as I said, that these are line segments. Line segments, that is what I'm representing is. So that means these are, it is something like say UV. If I call U and V are two vertices, they are distinct. So that means this is an edge. So we'll call these are edges. So this is an edge, this is an edge. So how many edges are there? So there are 4 plus 3, 7 edges. So each edge is a pair of vertices. Okay, pair of distinct vertices. So whatever I have written here, this is a graph. In fact, it is a special kind of. I'm talking about a simple graph. What is a simple graph? Now that's what I've said. V is a non-empty set, usually a finite set, finite graphs we talk about. So it's a non-empty set. And E is a collection of pairs of vertices. Okay, so pairs of distinct vertices. So that's a I mean that is a graph. Now we'll talk about something called directed graph. Okay, what is directed graph? So directed graph, you see that instead of this line segment, if they are directed, suppose that they are directed like this. Okay, they are directed like this. So then we call it is a directed graph. That means your edges are directed, and they are actually called. So here these are called edges. Whereas if I talk about directed, that means I can talk about something like an ordered pair UV. So ordered pair UV. So this is an element of V cross V. Okay. So then we call it is a directed. And there are also there are cases where is U and V are same. So this is, so then I have, so a directed this to itself. So it is something like a loop. So that is what we call. So these are loops. Okay, these are loops. So graphs and directed graphs. So that they are very okay. Near to each other. So I can look at a graph. I can look at a graph as a directed graph, but here this is I have, if I have U and V, they are two distinct vertices, and S is given by a two I mean two different. Okay, so say for example here, so I have one is, this is your directed arc. So these are called arcs. Okay. So when I have a directed edge, that is, those are called arcs. So I have an arc here, I have an arc here. So a pair of arcs, two directions, that can be thought as an edge in a graph. So that means a graph is a directed graph, but your edges, your arcs are symmetric. Okay. So both ways you have arcs. So that way you can think about a graph. Now, in a graph, we have various kind of things. So, for example, you can talk about an walk. Okay, walk means what? So, if I have suppose here, I'm here. So, I start going from here to here, here to here, here to here, here to here. So that means it is a finite sequence of vertices. So where the subsequent vertices, they are adjacent. When I say adjacent, I said two vertices are adjacent if there is an arc, or there is an edge between the two vertices. So we call them adjacent. So if I take a sequence of vertices where each subsequent these are adjacent, we call it an arc. And arc where it does not cross itself, then we call it a path. Okay? So the path means, so U1 to U2, U2 to U3, UK to UK plus 1, where none of these UKIs, intermediate UKIs, if they are distinct, then it is called a path. Okay? And what is a cycle? A cycle will be something like, so I start with this, and come back this. A path with the starting point and the end point, if are the same, then it is called a cycle. So these are very, elementary kind of definitions, and by the name itself, it is understandable how they are, what those objects are. So as we come across, whenever I come across a new term, I'll just explain that. So mostly they are understandable. So let me talk about something about a few things about matrix. Suppose A is some say m by n matrix. Okay, so it is m by n matrix. Okay. Now we talk about determinant of, right? So what is determinant of A represent? When we say determinant of a matrix A, what it is? So I take say 2 by 2 matrix. Suppose that I have a matrix AB. So let me write it A, B, C, D. So this is my matrix. So what do you mean by this determinant of? Okay. So you see, so for example, suppose that I have this C equal to say B equal to 0. B equal to 0. Now a matrix, a 2 by 2 matrix, if you see look at linear algebra, so a matrices, they are actually they correspond to functions. Okay, so if I have a 2 by 2 matrix, so if my A is this matrix is my A. Okay, so that means this matrix A will give rise to a linear transformation from say T from Rp to R. Okay, Rp to R. So how this T of X act? So you multiply this by X, where you take X is equal to, if you write say X1, X2, if you write your element as a column, then Ax is a 2 by 2 matrix. So this is again a 2 by 2, column with 2 entries. So that is again an element word, right? So that is a linear transformation. Now you look at, so if I take A is my this matrix, A0 CD, okay, A0 CD, then what is your this E1, where E1 will go to? E1 will go to the first column, your A0. You can easily see. Okay. Similarly, E2 will go to the CD. Okay. Now we look at this thing. So you see that I have here R2. I have here R2. Okay. I'm assuming just CD are positive orders. Okay. So this is my E1, right? This is my E2. Okay. This is if I take, so suppose, so where E1 goes? E1 goes to A0. Yes, suppose that this is my A0. And where is your E2 goes to? E2 goes to some CD. Okay? Suppose this is your CD. Okay? This one. Then to look at this one, if I consider this square, okay, so this E2. So this square, where this square will go? This will go to, if you see that because of linearity, you can see that this will go to this area. This is the image of this. Let me call this to be my S, okay, S. Then this is my your TS. You can easily check. Now see here, in this case, what I'm saying. So this is the image of my S. So what is the area of this one? Area of this one, you see that what is this? If I take A to be positive, then its length is equal to your A. So this is much A. And what is your height of this parallelogram? That is equal to D. So this is your D. Okay, so what is the area then? Area is AD. Of course, if I talk about, okay, area will be the modulus. And what is modulus of this? You see that if I take my matrix A to be equal to this one, matrix A is this, okay? Matrix A is this. So what is the determinant of A? Determinant of is A times D. That is equal to this. You can easily check it even if it is not. Okay, here what I took, I took my B, this B to be 0. Even if it is, okay, if in general, if you can easily check that if I take the image of this rectangle, this square, if this is going to be your something like this, so this is your image of E1, this image of E2, then this will be your, okay, image of, this is your image of S, then area of this area is nothing but the determinant of A, okay, modulus of this. Okay, so that is the area of this. So it is not just for 2 by 2 matrix, it is for 3 by 3 matrices again. Okay, and in fact, it is true for any n by n matrix. If we can talk about the volume, okay, the volume of a parallelepiped, okay, in a generalized situation. And there is a very nice exposition of this those who are not very, would like to see, so Professor Kumarason's book, that probably chapter 6. Chapter 6, there's a nice explanation of this determinant for very elementary way. So you can go through that. So that is what the determinant of a matrix means. But I'm not very, in fact, let me put a few. Someone has written this cross on my this thing. You can kindly remove that. Okay. Okay. So this is what the determinant means. Just I wanted to share. That is not my prime objective to discuss in this. I would like to talk about determinant in another sense. Okay, how you define determinant of a matrix. Okay, so say for example you take this matrix. Say take say A11, A12, A13, okay, A21, A22, A23. 831, 832, 832, 32, and 833. Suppose this is my matrix A. Okay? So when you talk about determinant of A, you see that there are 6 terms. If you expand this determinant, there will be 6 terms. Okay? And 6 terms, it will be something like, what is a term? A term will be something like A1 something, A2 something, A3 something. For example, you'll get say A11, A22, A33, that is one of the term in the expansion of the determinant. Similarly, you'll get A11, A23, A32, that is another term, right? So these are different terms. Now you see how many terms you get. You get 6 terms, okay? And 6 is equal to 3 factorial. Okay? And you see when you write down, when you write expand the determinant, okay, then you'll get 6 terms, and each term is something like a product of three entries. Okay, 3 entries. One is, what is this? Say what I'm writing, A1, one something like say A11 or A12 or A13, A21 or A22 or A23, A31, A32 or A33. Okay? So these are the 3 terms will come like this. Now see that your terms will appear. So these entries will appear in such a way that from each row, that means first row, second row, third row, you'll get one entries, and from each column you'll have. Okay, so you'll get something here, A1 something, A2 something, A3 something. Okay? And whatever you are getting, you should get exactly 1 ones, 2 ones, 3 ones. Okay? So that means, for example, what you'll get, say A12, A23, and A31. So this is one term. It will come. Okay? So you see that. So this is one row number 1, 2, 3, and column number. You see, column number is happening 2, 3, and 1. Right? Now this 2, 3, 1, it is nothing but a permutation of 1, 2, 3. Right? So essentially, those, you are aware of permutation, you can write this as a permutation. Okay? So this is, let me call it sigma. Sigma is a permutation of this. So this term is actually A1. What is 2? 2 is sigma 1. Okay? This 2 is sigma 1. 3 is sigma 2. 1 is sigma 3. Okay? So this is a term. And then what? Now here, this term will come either with a plus or a minus sign. Right? So that means it is a summation. It will be a summation of this, whereas it will come with some sum. Okay, so either plus or minus. Okay, it will come with this. And how many terms? As many different these permutations. So sigma, you call it Sn, is the set of all permutations of the symbols 1, 2, 3 up to n. Okay, and then you'll get all kinds of this. So here it is S3. S3 is all permutations of 1, 2, 3. Right? Sigma varying over all this. And then for each sigma, I'm getting one term like this. Okay? So 6 terms I'm getting. So what is this? This is your sigma 1. This is sigma 2. This is sigma 3. Okay? So this is how we are getting. But then I'm getting some sign. So in fact, you see that 3 of them exactly 3 of them are coming in with a plus sign and 3 with minus sign, right? So what are plus signs and what are minus signs? For example, if I take A11, then say A23, A32. How it is coming? So A11, then you see that while expanding the determinant, A11 into the determinant of this A22, A23, A32, A32, 33. So there, this A22, A33 minus A23, A32, right? So this one. So this term is coming with a minus sign. Okay? And what is this? The corresponding. What is your corresponding, your sigma? Sigma is 1 going to 1, 2 going to 3, and 3 going to 2. Okay? So this is actually what we call, it is 2 goes to 3 and 3 goes to 2 in terms of cycle decomposition. Okay. Again, I'll assume that we have some idea about permutations. Okay. So this is an odd permutation. Okay. What is odd and even permutation? Every permutation can be expressed as a product of these two cycles. This is a two cycle. Okay. So flipping, in fact, flipping. So number of flippings, if number of flippings is even, then it is an even permutation. Number of flipping is odd, it is odd permutation. So that means what? So this is coming with a permutation, and what kind of permutation? Permutation is odd permutation. Okay. So with this odd permutation, so this is, I'll take, so this is minus 1 to the power 1 or 2. If it is odd permutation, it is 1. If it is even permutation, this is 1. So that is known as the sign of sigma. Okay. Sign of sigma, if sigma is even permutation, it is 1. Odd permutation, it is minus 1. Okay. So let me just sum up. So what is determinant of A? Determinant of A, that can be written in this way. Okay, so there are different ways you define a determinant of a matrix. One is by induction. Okay, I mean 2 by 2 determinant. Then you by induction you define. Okay, so that definition and this definition, they are exactly same. So what is, let me write it. So all n by, now A is an n by n matrix. Okay, A is an n by n. So real or complex, whatever matrix it is. So it is a, so this matrix, n by n matrix, what is determinant of A? Determinant of A is given by this summation. You take the sign of this, okay? And then corresponding to sigma, there is a term, okay, 1, sigma 1, okay, and so forth, A n sigma n. Okay? So that means from each row you take one entry, from each column you take one entry, make the product. Okay? So that is a term in the expansion of the determinant. How many terms? N factorial terms, and each term will come with a plus sign or minus sign according as, that is this 1 going to sigma 1, the way you are choosing the column numbers along with rows, that is a permutation of the, okay, permutation of the set 1 to n. Okay, so that permutation, you take the sign of that, you put that sign as the sign of the term and take the summation of this. Okay, so that is how the determinant is expanded. Now let me see, where is there a connection? Is there a connection between your this determinant and some graph? Okay, now you see. So let's look at this. We talked about, say, this term. Okay, consider this term. Which term? I was considering this term. Okay. So let me go for this. So let me talk about this A11, A, okay, A23, A32. In 3 by 3 determinant. So this is a term. Okay. Now let me just you try to see what exactly I'm trying to do. Okay. I have Let me write in this 2 to 3. So this is my 1, this is 2, this is 3. Okay. So this term, you see that what I'm doing here. So I have, so if I talk about this, if I talk about this, what do you call this term of the determinant. Now here 1 1. So 1 to 1 I have put an arc. So this is an arc I have put. A 2 3, okay, A 2 3. So 2 to 3 I have put an arc here. A 3 to 2 I have put an arc here. Okay. So now see that this is a diagram. Okay. This is a diagram. This is a diagram. Okay. Now this diagram, if you see that this is corresponding to this term. Okay. Corresponding to this term. So here I have 3 arcs. So these are. So I have this. Now look at this stuff. So you can see that this one, it is actually this is a diagram, and what I see, this is actually disjoint union of some cycles. What cycle? First one I got one cycle with just length 1. This one is 2 2 3 3 2 2. That is another cycle of length 2. So this is disjoint union of cycles. Okay. So this kind of diagrams, so this kind of diagram is called a linear diagram. Yeah, that's the name. So diagram. Linear diagram. So what is a linear diagram? A linear diagram is one which is disjoint union of cycles. Okay. It is direct diagram. Okay. Disjoint union of cycles. Now, see why I'm talking, and then other thing. So this is coming from what? This is exactly coming from a permutation of 1 to 3. So which permutation for this one? Which permutation I had? I had 1 to 1, 2 to 3, 3 to 2. Okay. Now see, if I talk about cycle decomposition, then 1 goes to 1. So 1 goes to 1. This is cycle. 2 goes to 3, 2 goes to 3, and 3 goes to 2. So this is cycle. You see that exactly I have 2 cycles in the cycle decomposition of sigma, and corresponding to this I have 2 cycles in a graphical representation of that graph. So you can also call this to be a permutation diagram. It is essentially coming from a permutation. So it is a permutation diagram. Some people also call it linear diagram. Now you see that, okay, now you look at why I'm talking about this one. So you take say 3 by 3 matrix. You talk about its determinant. When I talk about determinant, now if I get, so I mean, see here, this is a term, whatever it is, this is a term. But point is, in many matrix, this term may not occur in the sense this term may be 0. When this term is non-zero, this term will be non-zero. In my determinant, this term is non-zero if each one of these A11, A23, and A32, these entries are non-zero. That gives me the idea. Suppose now I think carefully. I have a matrix. I have n by n matrix. So in principle, there are n square entries. Maybe that I have lots of zero entries. Okay? N square is quite a big number. Maybe there are many entries are zero entries. So I can talk about a zero non-zero digraph of the matrix. Okay, so let me define that. Okay, so I have A is sorry, n by n matrix. Okay, n by n matrix. Okay. So let me talk about say D. Say D is what? D is 0, 0 non-zero, 0 non-zero diagram. So what is your if diagram? Okay, I'm denoting as D. Digraph, there will be a vertex set. What is a vertex set? Vertex set is your 1 to up man. Okay? And what is your arc set? So that is okay, either equal E or A. What is your arc set? So arc set is equal to all those Ij, such that this Aij is non-zero. Okay. So all those entries. So therefore, you get a non-zero digraph. So I mean, you assume that I and J there is an arc, I to J there is an arc. Okay. So when if Aij is non-zero, so then what you see that then the determinant of this matrix can be written in this. I just take an example now. I think that will be more. Suppose I have something like this. Suppose my zero non-zero digraph is something like this. Suppose this. Okay. Suppose this one. So this is my 1. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay. Here that means these are symmetric. Essentially I have this. Have this. Suppose this. Suppose this. Suppose this. Sorry, this one, this. This. Okay. Suppose my matrix A is a 6 by 6 matrix. Okay. It is 6 by 6 matrix. And the zero non-zero entries, okay, the non-zero entries will give rise to this. This is my D of the matrix A. Now that means you see that if I talk about, so if, so what are the, how many non-zero terms in my determinant will be? You see that there are total 36 entries in the matrix, but how many non-zero entries? As many I have here. So let me make also, there may be also like something like this. Okay, there may be also something like this. Say 2, this also. There may be, I mean, diagonal entries. So I have this. Okay. Now you see how many non-zero entries are there. Total you have, so 2 to 4, 6, okay, 8, 9, 10, 11. Okay, 11. So there are 11 non-zero entries. Yeah. So all others are 0. So that means you see what are the terms you'll get. You'll get actually exactly say, I mean, one is see how many different ways you can have permutation diagram. One is if I have to cover this, I have to cover this. Okay, these two can be covered only by this. These two can be covered by this. These two can be covered by this. Okay. If this is the case, can you see that there is exactly one, that the determinant of the entire matrix has exactly one term. Why? Because you see that if I take A11 up to, okay, so A6, A1, sigma 1, and so forth, right? Sigma 6. If I take this, so there should be, so 1, okay, so 1 to this, there should be some, okay, something, so 1 to 2, then 2 has, yeah, if I take say 2 to 3, then I need, there should be disjoint union of cycles, so I have exactly this one only. I have only this one. So that means the entire determinant, I have only one non-zero term. What is that? This is your A12, A21, then A33, right? This is 33. See, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay. 33, A44, A56, A65. So these are only non-zero term I have. And then what will be? What will be the term with a positive sign or negative sign? Okay. Now see here, this is, I have this cycle. This cycle is an event cycle. Event cycle means event length cycle. So this is going to be an odd permutation. This is going to be an odd permutation. Okay. So these are your diagonal terms of this one. So this is odd and odd. So there are two cycles with even length. So that means it is two odd cycles, odd computation cycles are here. So this is this one, and this, therefore it is going to be your sine of this sigma. So sine of this sigma is going to be equal to 1. So that means determinant of this entire matrix, the matrix A, is going to be this one. Okay? So this is effectively can be used for what? For those matrices whose zero non-zero pattern you know. Okay? So this is just one small example how this digraphs, or graphs, they can come to come to play a role in your doing things in matrices. Okay, so let me go to some other thing. So this, it has just, I have introduced this idea, and using this idea there are a lot of things can be done. Lot of things are done. Okay. Not only about the matrix, determinant of this matrix, the what we call the characteristic polynomial. Okay. The generating the characteristic polynomial. These ideas can be effectively used. Okay. Let me go to the other side. Okay. So I have a graph. Given a graph G, there are a lot of several kinds of matrices are attached to a graph, okay, which gives rise to various uh, properties, various happenings in the graph itself, which are expressed, which can be checked, which can be understood in terms of the matrices itself. So matrices. So basically, I'd like to introduce a few matrices, okay, with respect to for a given graph. Given graph. Okay. So here I'm taking now simple graph. In fact, the same thing can be generated for more general kind of graphs, digraphs, and various things. So let me talk about simple graphs. That means here there is no direction on the this thing. Edges. Okay. Suppose you have a graph G. G has your, okay, G has a vertex at V and S at E. Okay. So it is something like you have your vertices and some edges. Okay. Suppose you have this one. Suppose this. So you have your, as I said, my vertices usually are set of natural numbers. Okay, so this is 4. And these are my edges. So I have 4 vertices, 3 edges. Now we talk about something called adjacency matrix. Adjacency matrix of G, okay, of G. So this you define as say A, or you can call A itself. A. It is what? It is a matrix of size what? This n by n. So this is say n is, so number of vertices is equal to n. Okay. So A is a matrix of order n by n. Okay. So your this one, these rows and columns, they are indexed by the vertices. Okay. So vertices your 1, 2 up to n. Okay. So vertices 1, 2 up to n. So here, if I call it say Aij, what is my Aij? Aij equal to Aij, as simple as that. It is your 1 if, sorry, let me call it I. This is a notation. That means I is adjacent to J. That is what adjacency it is. I is adjacent to J, then you call it 1, 0 otherwise. Okay. So this is a matrix. It is A. Now, what kind of graph I'm taking? I'm taking a graph which is simple graph. Simple graph in the sense that it has, the edges are not directed, so there are line segments. That means if for example, here 1 is adjacent to 2, then 2 is also adjacent to 1. Okay? There is an edge between 1 and 2. So A is adjacent to 2 implies 2 is adjacent. So I is adjacent to J implies J is adjacent. Okay? And I is never adjacent to each other. Okay? We have our edges are joining two distinct vertices. So that means this A is what? A is, first of all, A is a symmetric matrix. Right? Symmetric matrix what? Because I is adjacent to J implies J is adjacent. And secondly, your diagonal entries are 0. Okay? 0. So this is that kind of a matrix. Now see. So why is this adjacency matrix? In fact, this is fundamental. Suppose I have a graph. Okay? This graph, they appear in diverse field, diversity. But how do you store a graph in a machine? You cannot just draw something like this. So you have to, essentially what you have to do, you can store, okay, V. Okay, V you have, so what V's are points, okay, some points, maybe some objects. So that set V you can store in the machine. And you say all those pairs, okay, and what are edges? The unordered pairs. So when you take all set of all unordered pairs, that you can you can store that in the machine. But there is an effective way. This matrix A, if I take this matrix A, it exactly represents my graph G. Okay? Your, row numbers, column numbers, these are vertices. Okay? And what are your adjacencies? Those, if Aij is 1, then I2j adjacent is, otherwise no. Right? So it exactly describes your matrix. So for description of the matrix, description of the graph, this adjacency matrix is crucial. That this is a very elementary way of doing it, that mostly it is done this way. But is it the only way? It is the only thing that is helpful for? No. Lot of things about the graph are described by this adjacency matrix. Okay, let's just give a few examples. One is what? Okay, just to see one thing, that this because this matrix is symmetric, diagonal entries are 0. Okay, so that means trace is 0, right? Okay. Now here, suppose if I say, I take the, what is A square? Let's look at A square. A square is what? A square is, so your matrix A. Okay, so then A. So what is your, so if I take A square, the ijth entry of A square. Okay, how I'm getting it? So this is going to be, this is equal to sigma Aik, okay, Akj. Okay? K is varying from 1 to n. Right? So now here, so this fellow, this product is either 0 or 1. When it is 0, if one of them is 0, then product is 0. When it is 1, both of them are 1. So Ik is 1 and Ikj is 1. So you see here, suppose it is I, it is J, suppose it is K here. Okay, K here. So Ik is 1, that means there is an edge. Kj is 1, that means there is an edge here. Right? So that means what? So how many non-zero terms are there? As many ways you can go this to this. Okay. I to j, okay, via some k. So that many k's, as many k's which are, okay, which are common vertices adjacent to I and j, that will be the number of non-zero terms here, and that many ones here, right? So that means what? That means, so if I have a k such that Ik and kj, they are adjacent, that means I have a walk from I to k, k to j. So this is a walk of length 2. Okay? So that means this is equal to the number of walks. Number of what? Number of walks from I to j, walks, okay, walks from I to j of Okay, 2 steps of length 2, right? Length 2. So that means, so what the ij entry of a square will give me? That will give me the number of 2 walks, okay? Length 2 walks from I to j. That is your ij entry, right? Then what is your a I sorry, I mean what is your I entry? I at entry, okay, of this. So that means from I to j you go and you come back. So that is walk of blank 2. You'll go somewhere and come back. So how many? As many edges are there which are incident to I. That means as many vertices are there which are adjacent to this. So that is called the degree of this. Okay. So what is ith entry of this? That is the degree of degree of the vertex A. So that means this is, I can write here, the A square, the ith entry, this is equal to degree of I. Okay. Then if you can you, what about then AQ I to j? By the same logic, I to j, the number of walks of length 3. Okay, so 2 jumps. So length 3. So number of this, so this is equal to, so number of, okay, ij walks. Okay, I to j walks, that means walks of length 3. Okay. So then what is your a cube? A cube ii. A cube ii. It is going to be, that means you have, so you start from this, then you have to come back to I in, okay, 3 steps. So that means you have to go via a triangle only. Okay. So number of triangles. So this will be equal to number of triangles you can cover from this to this. So but see here, number of triangles with this as an edge. So you can come this way or you can come also this way, the other way. Okay. So this is, so let me, so number of triangular, okay, triangular walks from I to I. Okay. Then you tell me now. Now, then what is your trace? First of all, what is your trace of A? Trace of A 0, because all diagonal entries are 0. What is trace of A square? Trace of A square. Okay. So it is, so each one, so what we have seen, that this is A square ith entry is the degree of, okay. So then if I add all the degrees, every vertex has degrees. If I add the degrees, okay, so then that is sum of the degrees. Then does it have a link, relation with number of edges? You see that each edge of the graph will add to one degree to two of the vertices. Okay, this is an edge. So if I have an edge here, this is an edge. This edge will contribute to a degree of this and degree of this, 1 by a number 1 itself. So that means what? So this is nothing but the 2 times the number of edges. Okay. Similarly, what about your trace of A cube? Trace of A cube. Trace of A cube is equal to, now it's a number of triangles in your graph. So these are a subgraph of this type. A graph which is appearing this type is called a triangle. Okay, so how many triangles are here? So you see that from this vertex, I can have 2 triangular walks, okay, this way or this way. From each one, same triangle, I can have, will contribute to 6 triangular walks, okay, for 3 different vertices. So that means trace of A cube is equal to 6 times. 6 times number of triangles in G. Okay. So these are some very elementary this thing, relation of this adjacency matrix to along with the graph. So there are lots of, so there is vast this interaction between the graphs and these adjacency matrices. Some certain things just let me just mention. What kind of matrix is, as I have just said, is a symmetric matrix. And it's a 0, 1 matrix. So entries are only 0 and 1. 0, 1 matrix. It's a symmetric matrix. Okay. I have two things. One is your non-negative matrix. It's a non-negative matrix. And the other one is a symmetric matrix. For a real symmetric matrix, a very strong results are known, right? So because it is real symmetric, it is a diagonalizable matrix. What does it mean? It's all eigenvalues are real numbers, right? All eigenvalues are real numbers. Then the eigenvectors are orthogonal to each other. Okay, so it is unitarily diagonalizable matrix, and that is that the study of the graph properties and the eigenvalues and the eigenvectors of this adjacency matrix. Okay, there is a vast amount of studies, a lot of this interaction between this the spectrum, the eigenvalues, eigenvectors of this adjacency matrix, and the properties and the various things that happens in the graph. Okay? Various properties, graph theoretic structural properties of the graph. There are lots of interactions. So that just mention. I will not go to that. Just the advantage is that the graph, this matrix is a symmetric matrix, symmetric 0, 1 matrix, and it has that's right, very strong properties about the eigenvalues and eigenvectors. Let me talk about two other matrices related to a simple graph. Okay? I'll take another 15 minutes. Okay. See here. Again, I take, kindly clear the board. Someone has written here. Again, suppose say G. Say, okay. G is again a graph. Okay. So this time we talk about another matrix Q. This is called your incidence matrix. Okay. This incidence matrix, it is here you can call it directed incidence matrix. Let me give an example. Suppose I have just say this one and say this one. Okay. I have, so this is a graph. This is my simple graph. Okay. Now, so let me call it 1, 2, 3, 4. So this simple graph. Now what you do, you put directions to the edges. Okay. Whatever way. Okay. You can give directions to the edges. So this is called you orient the graph. So that's what it is called. Orient the edges by any orientation. So you give some directions to the edges. Now then this, so it has how many, say V has n points and how many edges are there. So yeah. Then this matrix is an n by m matrix. Q is an m by n matrix. Suppose you have this vertices, let me call it say V1, V2 up to Vn. And edges is your E1, let me call it E1, E2, En. Okay. So, right? Now, this E1, E2, En, these are edges, these are your vertices. So that means this matrix Q that I'm talking about, this is, the rows are indexed by the vertices and columns are indexed by the edges. Okay. And then suppose this matrix you call it say Qij. I is your I is your vertex, j is your column number. So what is your qij? Qij is equal to 0. Okay? If this is ej is my okay, is not incident to vi. That means vi is not a vertex of the edge. Okay? And it is your -1, okay, if this ej, okay, let me call it origins. Okay? That is known as, suppose this one 1 2 3 1 2 3. So this 1 3, that is an directed edge now. So it originates at 1, terminates at 3. So if ej originates at vi, then call it -1 and 1, okay, 1 if ej terminates, okay, terminates at vi. So this is your incidence matrix. Okay? So oriented one, which basically also this 0 1 incidence matrix is there. We have a purpose, that's why we have oriented, and we have taken a special kind of a matrix here. So for example, here what I have 4 vertices, 1 2 3 4. Okay, what is E1? This is, if I call it my E1, this is my E2, this is E3, this is E4. I have 4, this one also. So E1 is 1 2 3. So E1 will be -1 and 2 3, so 1 and then 0 0. Okay. Then E2 is what? This is my E1. E2 is my 2 to 1. So that means it is this -1, it is 1, it is 0 0 0, and so forth. Okay. So this is what is my incidence matrix. Just look at what kind of matrix you have. You take any column, so that is corresponding to some edge. So it starts at some vertex and ends at some vertex. So therefore there will be exactly a 1 -1 and 1. So column sum is equal to 0. Okay. Each column has 1 1 and 1 -1. So their sum is 0. So that means this is a matrix. This is a matrix. So column sum is equal to 0. So it's a singular matrix. Okay. It's a singular matrix. And if I remove any of the row, that row is actually, it is the negative of the sum of the all others. Because row sum is, sum of all the rows is 0. Okay. So this is why what is specialty about this? It has a relation with another matrix, which is very, very important or very, very well studied matrix corresponding to A graph Z. I'm going to introduce that now. So that has a very typical name. In fact, it has relation with Riemann surface, this Laplacian and all. So we'll not go into that, but the name comes from there, Laplacian. Laplacian matrix. What is Laplacian matrix? So Laplacian matrix of a graph Z, this is equal to, I have already talked about adjacency matrix. So let me call it AG. And then you take DG. What is DG? DG is, so DG means it is a diagonal matrix. Diagonal matrix D1, D2, Dn. Okay. So what is your DI? DI is degree of the vertex I. Okay. So if I have a vertex this, then how many? So this, for example, this one, then this vertex I has degree 3. So you take degree of each of I, okay, and then you take that your diagonal entries. That diagonal matrix is called DG. Okay, DG minus AG. So that means what is your LG? This LG is equal, if I call it say LIG, it is your again n by n matrix. Your vertex set has, okay, n vertices. So what is Lij? Lij is equal to your degree I, okay, di, if I is equal to j, right? And it is equal to 1 if I is adjacent to j and 0 otherwise. Okay. Now see, if I take adjacency matrix, Okay? If I take a row, the ith row, if I take ith row of the adjacency matrix, this is my adjacency matrix. In the ith row, how many ones are there? As many ones, as many, okay, corresponding to each j, such that I is adjacent to j, I have one there. So that means in the adjacency matrix, how many ones are there? Exactly the number which is degree of I, right? So then what I'm doing here, dg minus ag. So diagonal entry is degree, adjacency matrix is subtracted. So that means this what I have, this in LG has this property. Okay, this is row sum is 0. Okay, row sum is 0. Right? Row sum is 0, and so therefore, if row sum is 0, that means this is a singular matrix. Okay? Singular matrix. In fact, this is all one vector. Okay? So what is one? All one vector. This is a null vector of LG. Okay? So this is one. But the best part of this matrix is this LG. LG is equal to, I define that Q, no? This Q transpose, that is equal to LG. Okay, so let's see what is, so Q transpose. Let's see, Q transpose is what? If I take say ijth entry of QQZ. So what is that? So you see that I have this Q matrix. Okay, I have Q matrix. I take its, okay, transpose. So ith row, jth column. This jth column is actually jth row of it. Okay? So that means what? If I take, say, this is my, so let me call it QI. QI is what? QI is that ith row. Okay, ith row. And I take the jth row, their dot product. Okay, this row, ith row, jth row, you take. So you multiply and sum up. Okay, so that is called a dot product. Dot product of this. So dot product of this QI and QZ. So that is going to be your ij entry of this matrix, Q transpose. Right? Now you see here. So this, if I take two rows, if I take two rows in this matrix Q, this is my matrix Q. Okay, I take two rows. I take their dot product. What is that dot product? Dot product will be actually the common number. Okay, so the the common ones will be multiplied. Okay, so so when I take dot product, so some term, so these will be multiplied with a non-zero term, provided I get non-zero entry here. But that will be there provided there is an age there, and with that age there will be one some what I have. I'm taking I and j different. Suppose that I and j are two different rows in your Q matrix Q. I'm taking the dot product. Okay. So if I have a common non-zero entry here, non-zero entry common here and here, then one will be, there will be, okay. So there will be one, and there is another minus one. That means this should come from some age. Okay. So if there is some age there, so that means, so, and others, there cannot be anything else common here. Okay. If I and j are different, then if there is another common here, then another age will have these n points I and j, which is not the case. Okay. So that means there is exactly one distinct. So that means this is equal to, this is going to be equal to -1, because one of beta entry is 1, other is -1. If I and j are adjacent, I and j are different. If they are not adjacent, that means there will not be anything common. So it is 0. I and j are not adjacent. Okay, I is not equal to j. And third one, suppose that I and j are same. Okay, I and j are same. So I and j are same. Then that means what? How many times this a non-zero entry will appear? That will be squared up. Okay, I and I. So how many times? As many times that I appears as an endpoint of some edge. Okay, that is nothing but degree. So that means this is going to be your degree I. Okay, so that means the ijth entry of this matrix, ijth entry of this matrix is what? It is -1 if I and j are adjacent, I and j are different, 0 otherwise I and j are different, and if I and j are equal, then this is going to be equal to the degree of this. Essentially, that is what we talked about, this LG. Okay, so that means what? This is LG is equal to this matrix. Okay. And if you can see that this LG is a very nice matrix. So it is actually a positive semi-definite matrix. So what does it mean? That if I take X, now if you take say X is inside say Rn. Okay, X you are taking as a column. Then you consider X transpose this L X. Okay, so this is equal to X transpose, then L is your Q transpose, okay, times X. That means this is going to be your Q transpose X, then Q transpose X transpose here. Okay? This is your listing. Okay, so that means what? This fellow is what? This fellow, if I talk about Y, so this is equal to Y transpose Y. Okay? Q transpose is essentially it is an M by N matrix. Okay? So therefore this is. So this Y is inside Rn. So this is dot product of Y with itself. So that means this is greater than or equal to 0. That is what it is called, that L is a positive semi-definite matrix. Okay, L is a positive semi-definite matrix. However, you already know that it is L is a singular matrix, so it is definitely not going to be a positive definite matrix. A positive definite matrix is, there are many different criteria or different way of saying this, that characterization rather. So it is a symmetric matrix, real symmetric matrix. All its eigenvalues are non-negative. Okay, so then also that is, or it is at X transpose Lx is greater than or equal to 0 for every vector X. Okay, and I just end with two things. Why this L? How this matrix L helps? This L helps in a lot of ways. Okay? I mean, a second lecture probably would have proved a various result, something like this. What is that? Now this again, because L is positive semi-definite, so therefore its eigenvalues, again it's a real symmetric matrix, so all these are real. So suppose that 0 less than or equal to say this is your lambda 1. So lambda 1 is your first eigenvalue. Others are so lambda 2 and so forth, lambda n. You can order. Say I have ordered the eigenvalues of this matrix L. Okay. So first I know that the smallest eigenvalue is 0. What can you say about lambda 2? Now, with the help of this incidence matrix itself, you can very easily, derive. Okay, now I just sum up and not prove things. So very easily you can show that if my graph is connected means what? From anywhere to anywhere you can move by a path. Okay, so that is called a connected. A graph is connected if and only if this lambda 2 is non-zero. Okay? In fact, this how many zero eigenvalues are there? That means how many lambda is lambda 1, lambda 2, lambda k. If lambda 1, lambda 2, lambda k are 0 in this eigenvalues, okay, in the spectrum, this up to k, if lambda is a 0, then my graph has exactly k connected components. The number of connected components is the number of zeros as the eigenvalues of this Laplacian matrix. Okay, this is one thing. And there is one celebrated result. You know what? That you have this matrix L. You have this matrix L. Now so this is a square matrix. You just remove any row and that same column. That means you take a principal submatrix, that's called principal submatrix of L of size n minus 1. Okay? So that means you remove the last row and last column, or the first row and first column. Okay? You take the determinant. That determinant is constant. Whichever row and column you choose, it is immaterial. That determinant is going to be same, and that determinant is something called a number of spanning trees. Trees means what? You see that suppose I have, say for example here, if I talk about, okay, I say this one, this graph I talk about. So this graph is not a tree. If there is a cycle, then it is not a tree. Suppose I have a connected graph without a cycle, then this is called a tree. Now suppose I have a graph like this. This is my graph. In this graph, now I'm talking about the trees inside this. Say for example, if I consider say this is a tree because there is no cycle, it is a connected one. So that means how I connected this thing is, suppose that I want to keep minimum number of edges keeping the graph connected. That means it is I want to minimize my cost as less as number of edges inside the graph, but it should be connected. I should be able to move it. Okay. So how many different ways you can do that? That is the number of spanning trees. Spanning means all vertex should be covered, and tree means there should not be any cycle. Okay, and it is connected. So this number of spanning trees. For example, how many spanning trees in this graph? And you can easily count. So that number is essentially the determinant of the matrix obtained by deleting a row and the same column of the matrix A. That is a celebrated result called matrix tree theorem. Okay, so that is known as matrix tree theorem. So, these are only a few elementary connections between graphs and matrices. And in fact, this one more thing let me just mention that. So the practical use, one very practical use for this Laplacian is that, so what people do, suppose I have a big graph, lot many nodes. Now suppose that I want to break the graph into clusters. That means the vertices they are more near to each other. Okay, more near means more. There are lots of edges between them. Okay, so edges are clustered. So how to determine break the graph into these clusters is by the eigenvectors of this Laplacian, okay, Laplacian matrix. And which eigenvectors? Eigenvectors corresponding to the smaller eigenvalues, those eigenvalues which are near to 0. So first few non-zero eigenvalues. Of course, if it is connected, then you throw 0, and then all non-zero eigenvalues will remain. The smallest ones you take, a few smallest one, and they are used to determine the clusterings of this in a very effective manner. And there are a lot of applications in this. Even for the what do you call the adjacency matrix, its spectrum that was very effectively used for Google this search engine at the beginning. Now they have other things also. I think I should stop here. Yeah, thank you.
If there are any questions, then please let us know. Okay. If there are no questions from audience, then we will proceed further. On YouTube, there is one question. Someone has asked what reference book can be followed for this content.
Okay, yeah. Okay, should I? let me show them this one. Just a minute.
Sir, I have a question.
Yeah.
Did anybody explore what is the higher order submatrices represents? Means like 2 by 2 principal submatrices that represents number of edges. In fact, negative the number of edges. 3 by 3 number of triangles. Because
No, I mean,
what
yeah.
about 4 by 4 submatrices? Do they carry any information about the graph or
No, 4 by 4. Which 4 by 4?
principal submatrices? That's like you
Oh,
have
I
made
see.
a
I see.
trust, trace of the
Um,
symmetrics and
Wait. No. I mean, this is no. Those will be those. In fact, if you want to go for, suppose you want to go for the characteristic polynomial of the adjacency matrix, right? So definitely they will come into picture,
yes, they
right?
come.
So now you see that now you consider that set 3 by 3 submatrices how they appear, right? The 3 by in the determinant of 3 by 3 matrix triangles will only
Triangles.
appear, right? Triangles will appear. Now 4 by 4, how many ways? Either this there will be your square, I mean 4 cycle, right? Or a pair of disjoint, okay, 2 cycles,
Yeah, even
right?
K4 also may come.
No. I'm talking about this permutation something.
Okay.
In the when you talk about when you deal with the determinants, okay, when you talk about determinants and all, so then those kind of things will matter.
Yes.
That is one thing. So then you can effectively you can measure. To measure them, you can use this determinant of these matrices, right? Already you know the number of edges, okay? And if I know how many, I mean permutation subdigraphs or say, I mean linear subdigraphs or size say 4 are there, okay? Already you know how many 2 are there, right? So if you know 2 matchings, somehow if you can talk about 2 matchings, then subtracting all those 2 matchings from the total say 4 by 4 permutation submatrices, you know the 4 cycles, how many 4 cycles are there,
Yes.
right? So this is one thing, and I don't know. I mean, whether I could understand your question, but also other thing that you see that when I talk about the characteristic polynomial of a matrix, then what is the coefficient? Suppose that it is a p lambda. Lambda is my the variable in the characteristic polynomial. So what is the coefficient of say lambda to the power k? Lambda to the power k, the coefficient will be minus 1 to the power k times the sum of all n minus k size principal subminors.
Principal.
Okay. And then principal subminors, again they will come from, so a principal subminors will come from a subdigraph of the graph.
Yes.
Okay. So therefore you'll get all those linear factors will come into picture in that way, in the characteristic polynomial. Yeah. So let me just share. Uh, uh, is it visible?
Yes, it is visible.
Okay. So can you see there are these two.
Hmm.
One is Richard Bruel is one very fantastic book. I mean, this is not only on these matrices, also various aspects. So that is there. And graphs and matrices, it has is slightly, of course, I mean, those slightly involved, but very nice descriptions are there about these matrices, graphs and matrices by R.B. Bappat, published by, yeah, Springer.
Okay. Yeah. Are there any further questions? It seems that there are no more further questions. Then,
Yeah. Okay.
thank you, sir, for your excellent talk. It was really an interesting one. Now, before dispersing, I would like to request everyone for a group photo. Whoever can turn on your camera, please turn it on so that we can have a group photo. Okay. On the count of three, I will capture photograph. 3, 2, 1. Smile. One more. Okay. Thank you. Thank you, sir.
Thank
So,
you. Thank you.
with this, our first birthday talk comes to an end. Join us at 5 p.m. for another interesting talk. Thank you.
Thank you.